These are going to be notes on the derivatives of trigonometric functions. So generally when we want to do anything involving trig functions, we start with the f of x equals sine x function, just to get an idea of what its derivative will look like, and then we'll move on from there. So we're going to start with a graphical approach. This is not an actual proof of what the derivative of sine x is going to be, but it will give us at least an idea as to the direction that we're going to head. So what we're going to do is we're actually going to graph f of x equals sine x, and then go ahead and graph its derivative on the same set of axes. So the graph of sine x is here. Notice it is an odd function. It passes through the origin and it has symmetry with respect to the origin. It has maximums at pi over 2 and a 0 at pi, a minimum at 3 pi over 2, and another 0 at 2 pi. So what we're going to do is graph the derivative of this function. So we notice things like here we expect the derivative to be equal to 0 because it will have a horizontal tangent line. So we're going to get a 0 here. And then to the right of this 0, the slope of the tangent lines will be positive, so we expect the derivative to be positive. And here we expect the derivative to again be 0. After that, we expect the slope of the tangent lines to become negative, so the derivative will be negative all the way to where it's 0 again here. Okay? So when we draw that, it's going to look like positive back to 0, negative back to 0. Pardon my bad drawing. And then we can follow the similar idea here. If the derivative is 0 here, we expect the derivative to be negative here because that's the slope of the tangent line until you get to the 0, which is here. So it'll go something along these lines. So if you notice, this is starting to look awfully familiar as well. You get this oscillating function that passes through 0, 1 and has zeros at pi over 2 and 3 pi over 2 and has a minimum at pi. Well, we know a trig function that does that. It happens to be f of x equals cosine x. So it appears that the derivative of f of x equals sine x is going to be, that's supposed to be a prime, is going to be cosine x. Turns out we're going to be right. We need to do a little more rigorous proof to be sure, but that's what the graph is going to tell us. We can do the same thing for f of x equals cosine x and try and figure out what its derivative is going to be. Here's the graph of cosine x. It should look familiar. We just graphed it in the previous slide. It crosses the y-axis at 1, where it has a maximum there. So the cosine at 0 is 1, the cosine at pi over 2 is 0, the cosine at pi is negative 1, the cosine at 2 pi goes back to 0, etc. So we're going to graph the derivative of this one. So again, I'm going to pick up where I think the derivative is going to be equal to 0, and that's anywhere that it has a horizontal tangent line. So that's going to be here, here, here. In between these two zeros, the slopes of the tangent lines are going to be negative. In between these two zeros, the slopes of the tangent lines are going to be positive. In between, well, let me put in another 0 over here. Here's another horizontal tangent line. And in between these two zeros, the slopes of the tangent lines are positive. So I was kind of hoping that the derivative of cosine x would be sine x, and it's not. This is not the graph of sine x, but it is actually a little bit close. Remember, the graph of sine x actually looks like this. Well, notice the graph of sine x is above the x-axis here, but the graph we just drew is below the x-axis here. And then the reverse is true in between the pi and 2 pi. So what we notice is that the graph of the derivative that we just drew is a reflection over the x-axis of f of x equals sine x. Well, what causes reflections over the x-axis? Negatives cause reflections. So it appears that if f of x equals cosine x, then its derivative isn't sine x, but it is the opposite of sine x. So again, these are just graphical arguments. We're going to do a rigorous proof as well. So before we can do the rigorous proof, we actually need to go ahead and pick up two trigonometric limits. We need to look at the limit as x approaches 0 of sine x over x and the limit as x approaches 0 of cosine x minus 1 over x. Those two limits are imperative to actually being able to prove, well, what is the derivative of sine x? What is the derivative of cosine x? So in order to take a look at the limit as x approaches 0 of sine x over x, we're actually going to watch a video from Khan Academy. So you can either watch it here inside this presentation, or you can watch it, this video is available on YouTube, so you can find it there as well. But you need to watch this in order to be able to follow along with the proof of finding the derivative of sine x, and in order to answer some of the homework questions that we're going to have for this section. So here's the Khan Academy video.
Now that we have hopefully a decent understanding of the squeeze theorem, we'll use that to prove that the limit, I'll do it in yellow, the limit as x approaches 0 of sine of x over x is equal to 1. And you must be bubbling over with anticipation now, because I've said this so many times. So let's do it, and it's actually, we have to go obviously dig out our trigonometry, and it's actually a visual proof. So let me draw at least the first and fourth quadrants of the unit circle. I'll do that in magenta. Let's see. So let me see if I can. I should draw it pretty big. Let me see. I should draw it like quite big. Let me see. I'll draw it like that. It's close enough. And then let me draw the axes. So this is the x-axis, would look something like that. Sorry, that's the y-axis. There you go. And then the x-axis, something like that. That's our unit circle. There you go. Now let me draw a couple of other things. Let me draw a, well, it is a radius, but I'm going to go beyond the unit circle. So let's go like right there. And draw a couple of more things just to set up this problem. Nope, that's not what I wanted to do. I wanted to do it right from this point. Right like that. And then right from this point, I want to do this. And then I want to draw another right from that point. I'm going to do that. And now we are ready to go. So, what did I say? This is the unit circle, right? So if that's the unit circle, what does it mean? It's a circle with radius of 1. So the distance from here to here is 1. And now if this is an angle x in radians, this is angle x in radians, what's the length of this line right here? What's the length of that line? Well, by definition, sine of x is defined to be the y-coordinate of any point on the unit circle. So this is sine of x. Right? So this is sine of x. I'm going to run out of space. So let me draw an arrow. So this is, that right there is sine of x. Now let me ask you a slightly harder one. What's this length right here? What's this length? Well, let's think about it. What is tangent? Let's go back to our SOHCAHTOA definition of tangent, right? TOA. Tangent is equal to TOA, opposite over adjacent, right? So what is a tangent of x? Tangent of x, well, it would be equal to, we could take this, it would be, if we say that this is the right triangle, it would be this length, the opposite, over the adjacent, right? So let's call this length over here, let's call this O for opposite. But what's the adjacent length? What's this base of this larger triangle? Well, this is a unit circle, right? So the distance from here to here, that distance is also going to be 1, right? Because it's just a radius again. That's 1. So opposite over adjacent is equal to the tangent of x, but opposite over adjacent is just 1, right? So the opposite side, this side right here, it's going to be equal to the tangent of x. Or another way of saying it, tangent of x is equal to this side over 1, or tangent of x is equal to this side. So let me write that down. That side is equal to the tangent of x. Tangent of x. Now, let's think about the area of a couple of parts of this figure that I've drawn here. And maybe I should have drawn it a little bigger, but I think we'll be able to do it. So first, let me pick a relatively small triangle. So let's do this triangle right here. I'll trace it in green. So this triangle that I'm tracing in green, what is the area of that triangle? Well, that's going to be 1/2 times base times height. So it's 1/2 times the base, which is 1. Right? It's this whole triangle. And then what's the height of it? Well, we just figured out that this height right here, that this height is sine of x times sine of x. So that's this green triangle here, right? Now, what is the area of not that green triangle? Let me do it in another color. Let me do it in, I'll do it in red. What is the area of this pi? This pi right here. That pi. Hope you see it. Well, that's not a different enough color. So this pi right here. Or I'm going there, and then I'm going on the arc. So it's a little bit bigger than the triangle we just figured out, right? It's always going to be a little bit bigger because it includes this area between that triangle and the arc, right? What is the area of that arc? Well, if this angle is x, right? It's x radians. What fraction of that is that of the entire unit circle? Well, there are 2 pi radians in a total unit circle, right? So this area right here is going to be equal to what? It's going to be equal to the fraction x is of the total radians in the unit circle, right? So it's x radians over 2 pi radians in the entire unit circle. So that's kind of the fraction that this is of, if you did it in degrees, the fraction that this is over 360 degrees, times the area of the whole circle, right? This tells us what fraction we are of the circle, and then we want to multiply that times the area of the whole circle. Well, what's the area of the whole circle? Well, area is pi r squared. The radius is 1, right? So the area of the entire circle is just pi. Right? Pi r squared, r is 1, so the area of the circle. So the area of this wedge right here is just going to be equal to, these pi's cancel out, is equal to x over 2. So that first small triangle, that was just that green triangle we did, is sine of x, 1/2 sine of x. That's the area of that green triangle. Then the slightly larger area of this wedge is, we figured out just now, is x over 2. And now let's take the area of that larger triangle, of this big triangle here. And that may be the most obvious. It's 1/2 base times height, so that's 1/2. The base is 1 again. 1 times the height is tangent of x. It's equal to 1/2 tangent of x. Now, it should be clear, just looking at this diagram, no matter where I drew this top line, that this green triangle has a smaller area than this wedge, which has a smaller area than this large triangle, right? So let's write an inequality that says that. The green triangle, the area of the green triangle, so 1/2 sine of x, that's the area of the green triangle. It's less than the area of this wedge, so that's x over 2. And they're both less than the area of this large triangle, right? Which is 1/2 tangent of x. Now, when is this true? This is true as long as we're in the first quadrant, right? As long as we're in the first quadrant. It's also almost true if we go into the fourth quadrant, except then the sine of x becomes negative, the tangent of x becomes negative, and x becomes negative. But if we take the absolute value of everything, it still holds in the fourth quadrant, right? Because if you go negative, as long as we take the absolute value, then the distances still hold and we still have positive areas and all of that kind of things, right? So my goal is to take the limit as x approaches 0, and I want to take the limit, in order for this limit to be defined in general, it has to be true from both the positive and the negative side. Let's take the absolute value of both sides of this. And hopefully this makes sense to you. If I were to draw the line down here, and this would be the sine of x, and that would be the tangent of x, as long as you took the absolute value of everything, you're essentially just doing the same thing as in the first quadrant. So let's take the absolute value of everything. And that shouldn't change anything. Especially if you're in the first quadrant, and you might want to think about it a little bit, why it doesn't change anything in the second quadrant. So we have this inequality, and let's see if we can play around with this. So first of all, let's just multiply everything by 2 and get rid of the 1/2s, right? So we get absolute value of sine of x is less than absolute value of x, which is less than the absolute value of the tangent of x. I hope I didn't confuse you by taking the absolute value. That original inequality I wrote was completely valid in the first quadrant, but since I want this inequality to be true in the first and fourth quadrants, because I'm taking the limit as x approaches 0 from both sides, I put that absolute value there. So you could draw the line down there and do everything we did up there in the fourth quadrant, but just take the absolute value and it should work out the same. Anyway, back to the problem. So we have this inequality, and I'm running out of space, so let me erase some of this stuff up here. Erase, erase. Nope, that doesn't erase. Okay, that should erase. Okay. So we could erase everything that took us so far, just so we can't forget this, though. This gives us a lot of space. Okay. So let's take this, and let's take that expression and divide all of the sides. It has 3 sides, left, middle, and right. Let's divide them all by the absolute value of sine of x. And since we know that the absolute value of sine of x is a positive number, we know that these less than signs don't change, right? So let's do that. So the absolute value of the sine of x divided by the absolute value of the sine of x, well, that equals 1, which is less than the absolute value of x divided by the absolute value of sine of x, which is less than, what's the absolute value of so all I'm doing is I'm taking the absolute value of sine of x, absolute value of sine of x, absolute value of sine of x. So what's the absolute value of the tangent of x divided by the absolute value of sine of x? Well, tangent is just cosine over sine, right? Oh, sorry, it's just sine over cosine. So that's equal to, so just do this part right here. That's equal to sine over cosine divided by sine. And you could say that this is the same thing as the absolute value of the absolute value divided by the absolute value. So what are you left with? Well, you're just left with 1 over, this cancels out with this, that becomes a 1 over the absolute value of the cosine of x. So you might feel we're getting close, because this looks a lot like this, it's just inverted. So to get to this, let's invert it. And to invert it, what happens? Well, first of all, what happens when you invert 1? Well, 1 over 1 is just 1. But when you invert both sides of an inequality, you switch the inequality, right? And if that doesn't make sense to you, think about this. If I say 1/2 is less than 2, and I invert both sides of that, I get 2 is greater than 1/2. Right? So that hopefully gives you a little intuition. So if I'm inverting all of the sides of this inequality, I have to switch the inequality signs. So 1 is greater than absolute value of sine of x over the absolute value of x, which is greater than absolute value of cosine of x. Now let me ask you a question. The absolute value of sine of x over, well, first of all, sine of x over x. Will there ever be a time when sine of x over x is in the first or the fourth quadrant? Is there ever a time that sine of x over x is a negative expression? Well, in the first quadrant, sine of x is positive and x is positive. So a positive divided by a positive is going to be positive. And then in the fourth quadrant, sine of x is negative, right? Sine of x is negative, y is negative, and the angle is negative, so x is also negative. So in the fourth quadrant, sine of x over x is going to be a negative divided by a negative, so it's going to be a positive again. So sine of x over x is always going to be a positive. So the absolute value signs are kind of redundant, right? So we could write 1 is greater than sine of x over x. And the same logic in the first and fourth quadrants, and that's where we're dealing with. We're dealing with, minus pi over 2 is less than x, which is less than pi over 2. So we're going from minus pi over 2 all the way to pi over 2. So we're in the fourth and first quadrant. Is cosine of x ever negative? Well, cosine is the x value, and the x, by definition, in the first and fourth quadrants, the x value is always positive. So if this is always positive, we can get rid of the absolute value signs there and just write that. And now we are ready to use the squeeze theorem. And let me erase all of this down here now. So let me ask you a question. What is the limit as x approaches 0 of the function 1? Well, the function 1 is always equal to 1. So I could have said the limit as x approaches infinity, the limit as x approaches pi, anything. This is always going to be equal to 1, right? So as x approaches 0, this is equal to 1. And then what is the limit as x approaches 0 of cosine of x? Well, that's easy too. As x approaches 0, well, cosine of 0 is just 1. As you get, it's a continuous function, so the limit is 1. So we are ready to use the squeeze theorem. As we approach 0, as x approaches 0, this function approaches 1, this function approaches 1, and this function, or this expression, is in between the two. And if it's in between the two, this is approaching 1 as we approach 0. This is approaching 1 as we approach 0, and this is in between them, so it also has to approach 1 as we approach 0. And so we are using the squeeze theorem based on this and this, and you could say, therefore, by the squeeze theorem, because this is true, and this is true, sine of x over x, the limit as x approaches 0 is equal to 1. So hopefully that gave you the intuition that you can kind of, another way to view it is as this line gets smaller and smaller as it approaches 0, as x approaches 0, that this area and this area converge, so the area in between kind of has to converge to the both of them. And if you want to see it graphically, I've graphed it here. Let me see if I can graph this thing. Show you the graph, just so you believe me. So we said that 1 is always greater than sine of x, which is always greater than cosine of x, between negative pi over 2 and pi over 2. And of course, this isn't defined at x is equal to 0, but we can figure out the limit. So there we have it. This blue line right here, that's the function 1. That's y is equal to 1. This light blue line right here is cosine of x. And this is the graph of sine of x over x. And you can see that, I've actually typed it in. So sine of x over x between negative pi over 2 and pi over 2, or the fourth and the first quadrants, the red line is always in between. It's always in between the dark blue and the light blue line. And so this is just an intuition of what happens with the squeeze theorem. We know that the limit as this light blue line approaches 0 is 1, and we know the limit as this top dark blue line approaches 0 is 1, and this red line is always in between it, so it also approaches 1. So there you have it. The proof, using the squeeze theorem and a little bit of visual trigonometry, of why the limit as x approaches 0 of sine of x over x is equal to 1.
Okay, so as I said, that proof gets a little lengthy, but the moral of the story is that when you're looking at the limit as x approaches 0 of sine x divided by x, you do in fact get 1. That's one of the two trig limits that we needed. The second one won't be nearly as long to prove. We will prove that one algebraically. So to find the limit as x approaches 0 of cosine x minus 1 over x, we're actually going to use a little math trick. We're going to take our limit, and what we're going to do is we're going to multiply the numerator and the denominator by cosine of x plus 1. Okay, it's a well-chosen one, so algebraically it's legal to do that. So when we do that, notice what we're going to get. We'll have the limit as x approaches 0. In the numerator, we do a FOIL, so we'll get cosine squared x, and then we'll have plus cosine x minus cosine x, so those cancel each other, and then we have minus 1 over x times the cosine of x plus 1. Okay, so when we go to simplify this, we want to keep in mind we're going to use this identity, the whole sine squared x plus cosine squared x equals 1. Pretty much the most used trig identity there is. And what I notice is up here in the numerator, I've got a 1 and a cosine squared x. So if we think of this instead as sine squared x equals 1 minus cosine squared x, notice that's not exactly what we have here. In our numerator, the 1 is negative and the cosine is positive, and I have the exact opposite of that in this identity. Well, to fix that, all I do is take a negative of both sides. So that numerator is not equal to sine squared x, but it is equal to the negative of sine squared x over x times the cosine of x plus 1. Okay, so the reason that we have that is, if you notice, sine squared x is just sine x times sine x. So I'm going to take the negative. It's just a constant negative 1. So I'm going to pull that out front. So I have the negative. I have the limit as x approaches 0. And I'm basically going to make use of the limit that we just proved. What I'm looking for is to have a sine x divided by x. Well, I have 2 sine x's in the numerator, and there's my x in the denominator. So I'm actually going to just rewrite this a little bit. I'm going to put sine x over x, and then up in the numerator, I still have another sine x, and in the denominator of that one, I'll put the cosine x plus 1. So I've just rewritten what we're taking the limit of to be a little more familiar. And by properties of limits, I'm able to split those limits across multiplication. So this is equal to the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of sine x over cosine of x plus 1. Okay, so I have a negative. This is the limit that we just watched the really long video for. That limit as x approaches 0 of sine x over x, that's equal to 1. And then this limit, the limit as x approaches 0, what we're going to do is try direct substitution. With this kind of function, as long as you can plug in 0, meaning it has to be in the domain of the function, direct substitution is legal for this. And sure enough, if you plug in 0, the sine at 0 is 0, the cosine at 0 is 1 plus 1. So what we get is the negative of 1 times 0, also known as 0. So in conclusion, that tells me that the limit as x approaches 0 of the cosine of x minus 1, all divided by x, is going to be equal to 0. Now that we have those two limits, we can actually prove that the derivative of sine x is in fact going to be cosine x. Let's take a look. So when we want to find the derivative of f of x equals sine x, we start off with our limit definition. So we have the limit as h approaches 0, f of x plus h minus f of x all over h. And we apply that specifically to the function we're working with, which is sine x. So f of x plus h says plug x plus h into the function you're working with. So that's the sine of x plus h minus f of x, which is sine x, all divided by h. So here's where we're going to start to run into some issues trying to find this. Generally, with the other limits we've worked with, what you're looking to do is somehow manage to cancel this h so that you can directly substitute 0 in place of h. Well, if you look at that numerator, there's pretty much not going to be a way to just cancel out an h because of the fact that we're dealing with a sine function. So we're going to have to get a little more creative. So we use the trig identity for sine of x plus h, which says sine of x plus h is actually sine x cosine h plus cosine x sine h. That's one of our trig identities. We still have minus sine x from the original and all divided by h. So what we're going to do is we're going to split this up to be in our better interest. We're going to take the sine x cosine h and the minus sine x and put those over h, and then split off the cosine x sine h over h. These two are equivalent, but we've chosen to split them into two separate fractions. And the reason we've chosen to do that is because the first fraction, you now have a sine x in common in your numerator, so we'll factor it out, and we're left with cosine h minus 1 over h. In the second one, there's nothing in common, so we're not really factoring it out, but I'm starting to notice, see the sine h and the h, and notice we're letting h approach 0. We're starting to resemble that first limit that we talked about. So once we split those off, this is what we end up with. Properties of limits say that we can split this first limit across multiplication. So we have the limit as h approaches 0 of sine x times the limit as h approaches 0 of cosine of h minus 1 over h. And then plus, split it again across addition, the limit as h approaches 0 of cosine x times the limit as h approaches 0 of the sine h over h. Okay. So what does this tell me this all equals? Well, we just spent time talking about the fact that this limit, as h approaches 0, sine h over h is going to be equal to 1. On the last slide, we just showed that the limit as h approaches 0 of cosine h minus 1 over h is actually equal to 0. Now, there were x's in here instead of h's, but as long as every x is replaced with an h, it's the same limit. So really what I need to take a look at are these two limits. So notice this is the limit as h approaches 0 of the sine of x. As far as this limit is concerned, h is our variable. It is, if you could directly substitute 0 in for something, you'd be plugging it in for h. Well, the only variable in here is x. So if h is the variable for the limit, and this is sine x, as far as this limit is concerned, there's no place to plug 0 in for h, which makes sine x a constant according to this limit. So what is the limit of a constant? Well, it's just that constant. So we get sine x times 0 plus the same thing happens for this limit. The limit as h approaches 0 of cosine x, there's no h in cosine x. So as far as that limit is concerned, cosine x is a constant, and that's going to be multiplied times 1. We'll notice this is sine times 0, which is 0, so in the end we end up with cosine x. So the moral of the story is that when you take the derivative with respect to x of sine x, you do in fact get cosine x. We can go through a similar process to show that yes, in fact, the derivative with respect to x of cosine x is in fact negative sine x, but I think I'll leave that for a homework exercise. We'll just take it for granted for the moment. What we now want to do is find the derivative of tangent x using the derivatives of sine x and cosine x. And what you have to keep in mind in order to do this is that tan x is sine x divided by cosine x. So what we're actually looking to find is d dx of sine x over cosine x. Now that we know the derivatives of sine x and cosine x, we can actually just use our differentiation formulas to find the derivative of tan x. So what rule are we going to have to apply to this function? Well, we're going to have to use quotient rule. So to find this derivative, we need the denominator times the derivative of the numerator, and remember the derivative of sine x is cosine x, minus the numerator times the derivative of the denominator, and the derivative of cosine x is negative sine x, and that's all over the denominator squared, so cosine squared x. So in your numerator, you're going to get cosine squared x, and then that'll be plus sine squared x, all over cosine squared x. And no, the cosine squared x's don't cancel, but what we can use is a trig identity. What is the sine squared x plus cosine squared x? That's just 1. So what we get is 1 over cosine squared x, and by reciprocal identities, that tells us that this derivative should be secant squared x. So as it turns out, the derivative of tangent x is actually secant squared x. So we could repeat this process for any of the other trig functions. I mean, if we wanted to find, for example, the derivative of secant x, we could instead treat it as 1 over cosine x and then use quotient rule to take the derivative of this, and that would give us the derivative of secant x. So once you have the derivative of sine x and cosine x, all of the other derivatives of the other trig functions naturally follow using quotient rule. So we'll skip that process, leave some of that for your homework, and here we go. So the derivative of sine x is cosine x, the derivative of cosine x is negative sine x, and the derivative of tangent x is secant squared x. Those are the three we just did. Here comes the other ones. The derivative of cosecant x is negative cosecant x times cotangent x. The derivative of secant x is secant x times tangent x. And the derivative of cotangent x is negative cosecant squared x. These are the 6 derivatives of trig functions. You are going to want to have these strongly memorized for any assessments that you might be taking, be they quizzes, homeworks, or exams. We use these frequently. So let's do some examples of these. We're going to find the derivative of f of x equals x minus tangent x. So our derivative, this is just the difference of two functions, so we'll just use the difference rule, which says I can take the derivative of each term individually. So the derivative with respect to x of x is 1, and we just said the derivative of tangent x is secant squared x. So that's the derivative of x minus tan x. Pretty straightforward for that one. Find the derivative of f of t equals t times secant t. So we've switched the variable, but it doesn't switch the rule. What operation is going on between the t and the secant t? It's a product. So when we go to take the derivative, f prime at t or df dt, what we need to use is product rule. So we can take t times the derivative of secant t, which we just said on the last slide, is secant t times tangent t, plus the derivative of t, which is 1, times the second function, which is secant t. And you can do some things like, hey, I can factor out a secant t, but it's not absolutely necessary for this particular problem. So I'll just rewrite it as t secant t tangent t plus secant t. If you want to factor it out, that's fine. Let's find the derivative of f of theta equals secant theta divided by 1 plus tangent theta. So again, we want to decide what rules we need, and because I'm seeing a quotient here, I'm going to use quotient rule. So f prime at theta will be the denominator, 1 plus tangent theta, times the derivative of the numerator. The derivative of secant theta is secant theta tangent theta, minus the numerator, which is secant theta, times the derivative of the denominator. Well, the derivative of 1 is 0, and the derivative of tangent theta is secant squared theta. And then that will all be over 1 plus tangent theta, that whole quantity, squared. There are many correct ways to go about simplifying this, and many different ways that, assuming it's equivalent, are perfectly legitimate and perfectly correct. I'm going to go ahead and factor out a secant theta out of both of those terms in that numerator, this being the first term and this being the second term. In my first term, I'm left with tangent theta times 1 plus tangent theta. And in my second term, I'm left with secant squared theta. And that's all over 1 plus tangent of theta squared. And I'm not seeing anything profound that can cancel. So you could do things like distribute this tangent theta to both of these terms. But unless something's going to cancel, some of those simplifications are unnecessary at this point. So we'll just leave it like this for now. Find the equation of the tangent line to the curve y equals tangent theta secant theta at theta equals pi over 4. So we're looking to find the equation of the tangent line. So the two things we need are a point and slope. Technically, we don't have the point. What we have is a theta value That's my independent variable. That's what's being inputted into my function. So I actually don't have the output at this point. So I'm trying to figure out the ordered pair. I know the first coordinate is pi over 4. I need the second coordinate. In order to find the y value, I just plug pi over 4 in. So y is going to be equal to the tangent of pi over 4 times the secant of pi over 4. So the tangent at pi over 4 is 1. And the secant at pi over 4, remember that's just 1 over the cosine of pi over 4. The cosine at pi over 4 is square root of 2 over 2. So when you simplify this, you get 2 over the square root of 2, also known as the square root of 2. So the ordered pair I'm working with is pi over 4 square root of 2. So that's my point. Now what I need is the slope of the tangent line, and this is where the derivative is going to come in. So when I'm going to find this derivative, this is dy d theta, okay, the derivative of y with respect to theta. This is going to be a product rule because I see a multiplication in between my tangent theta and secant theta. So I will have the tangent of theta times the derivative of secant theta, which is secant theta tangent theta, plus the derivative of tangent theta, which is secant squared theta, times secant theta. So if we clean that up a little bit, dy d theta is actually secant theta tangent squared theta plus secant cubed theta. Okay. So this gives me the slope of every tangent line. For any theta, this is the derivative. This is the slope of the tangent line. Well, I don't want the slope of every tangent line. I specifically want the slope of the tangent line when theta is equal to pi over 4. Okay? What I get is the secant at pi over 4, which we had just said is the square root of 2, times the tangent at pi over 4, which is 1, squared, and then plus the secant of theta, which we just said is the square root, the secant of pi over 4, which we just said is the square root of 2, and we're going to cube that. So what we get is the square root of 2 plus the square root of 2 cubed, which if you choose, you can rewrite that as the square root of 2 plus 2 square root 2. Because when you cube the square root of 2, it's the square root of 2 times the square root of 2 times the square root of 2. 2 of those are going to give you 2, which means you have a total of 3 square root 2's. So that's the slope. So when we go to write the actual equation of the line, it's y minus the y value, which we said was the square root of 2, equals the slope, which is 3 square root 2, times x minus the x value, which is pi over 4. You could solve this for y or not. Okay, let's find the 27th derivative of f of x equals cosine x. Now at first that may be a little intimidating to find the 27th derivative, but rest assured there's a trick. So what we do is if we start with f of x equals cosine x, and we just start taking the first few derivatives, let's see if we can pick up a pattern of some kind. So if f of x equals cosine x, the derivative of cosine x is negative sine x. Well then the next derivative, the second derivative, the derivative of just sine x is cosine x. So with the negative involved, the second derivative will be negative cosine x. Your third derivative, the derivative of cosine x is negative sine x. So with this negative paired with it, that's going to be positive sine x. Let's do another one. The fourth derivative of f with respect to x. Remember, once you get to the fourth derivative, you stop using the tick marks and you start using the 4 in parentheses. So the derivative of sine x is cosine x. And notice that's going to take us right back to cosine x. So what we're going to notice is that every fourth derivative is just going to bring us right back to cosine x. So for example, the fifth derivative is negative sine x. Sixth derivative is negative cosine x. Seventh derivative is sine x. Eighth derivative will be cosine x. So what we want to do is say, okay, every derivative that is a multiple of 4 is going to be cosine x. Well, we're looking for the 27th derivative. So there's a couple of ways to think about this. I know that the 24th derivative, because 24 is a multiple of 4, the 24th derivative is going to be cosine x. So I can just count from there. That tells me that the 25th derivative is going to be negative sine x. The 26th derivative is going to be negative cosine x, which tells me that the 27th derivative is going to be sine x. The other way to do this is to start at the 28th derivative, which is also a multiple of 4. Know that that is cosine x, and simply go back by 1 to get to your 27th derivative. So the 27th derivative of f of x equals cosine x is going to be sine x. Let's take a look at a couple of limits. Just to warm us up, let's keep in mind, if we want to find the limit as t approaches 0 on sine t. Sine t is continuous at 0, so it's eligible for direct substitution. This is literally just the sine of 0, also known as 0. If you're looking for the limit as x approaches 0 of cosine x, it's also continuous at 0. So this will be the cosine of 0, also known as 1. Those we're used to. So let's take a look at this one. This is find the limit as x approaches 0 of sine of 7x divided by 4x. Now this is not continuous at 0. We cannot use direct substitution to calculate this limit, so we're going to have to get a little more creative. What we're going to do is hearken back to that limit that we spent so much time on. The limit as x approaches 0 of sine x divided by x is equal to 1. Okay. So instead of thinking of x as x, it doesn't have to specifically be x. It can be anything. If you have a limit as something, I'll call it smiley face, approaches 0, and you have the sine of that smiley face divided by the smiley face. It doesn't matter what it is as long as it's inside your sine function, it's in the denominator of the function, and that is what is approaching 0. Then this limit will be equal to 1. So notice in our problem what we have is the sine of 7x. We can't easily manipulate the 7x because it's inside our sine function. So what I'd really like to have here is the sine of 7x not divided by 4x, but instead divided by 7x. If I could get this to say, if this said, the limit as x approaches 0 of sine of 7x divided by 7x, I know what that limit is. That limit is 1. But it doesn't say that. But wouldn't it be nice if I could kind of force it or manipulate it into saying that? So really what I want to do is say, okay, I want to turn 4x into 7x. What can I multiply by, call it c, to make 4x times that thing equal to 7x? Well, then this just becomes equation. If you can see what you should multiply by, fantastic. You do not have to set up an equation. But if you divide both sides by 4x, notice on this side you're just left with c, and on this side the x's cancel, and you get 7/4. So if you multiply this 4x times 7/4, it's going to magically turn into 7x. Now, that being said, you can't just multiply 4x times 7/4 because you feel like it, right? It's not an equation. You don't have a left side and a right side, and you need this to stay equivalent. But we can also say, hey, as long as you multiply the numerator by 7/4 as well, it's legal. This is a completely correct algebraic step to take. And what we're going to get is the limit as x approaches 0. In your denominator, you're going to get exactly what you were trying to get, which is 7x. And in your numerator, you're going to have the sine of 7x. Remember, the 7/4 cannot multiply times the 7x because that is inside your sine function. So I'm going to put the 7/4 out front of the sine function. Well, by properties of limits, this is just the limit as x approaches 0 of 7/4 times the limit as x approaches 0 of the sine of 7x divided by 7x. And we just said we know what this limit is. This limit is 1. And the limit of a constant is the constant. So in other words, this limit is equal to 7/4. And that's our notes on the derivatives and some limits of trigonometric functions.